Hello everyone, welcome to the 26th episode of the series. In this video, we'll talk about basis and dimension. So last time we saw the definition of a basis for a subspace V. So a basis for a subspace V is a linearly independent spanning set of V. Note that this definition can also be reduced to the following condition that we call a set of V, a basis for V, if every element of V can be written as a linear combination of uh, vectors in this set in exactly one way. In the same fashion, we have conditions for a spanning set for V and a linearly independent set. So, if every element of the subspace V can be written as a linear combination in at least one way, we call the set in concern a spanning set for V. And if we can write every element of V as a linear combination in at most one way, then we call this set a linearly independent set. So note that there's a relationship between the linear combination of R vectors and a matrix expression. So we can write this linear combination of V1 through VR as the product of the matrix of concatenation of the R vectors and the vector of coefficients. So with this in mind, the three properties that we just saw can be rewritten in the following manner. So if V1 through VR are vectors in a subspace V, and A is the concatenation matrix of these vectors, then the set V1 through VR is a spanning set for V. For each B in V, the equation AX equal to B is consistent. So there is at least one solution. A linearly independent set, if for all B in V, the equation AX equal to B has at most one solution. In other words, A has rank equal to its width, which is the same as the number of vectors. And the set basis for V, if for all vectors B in V, the equation AX equal to B has a unique solution. Let's understand this with the help of an exercise. So we're given a subspace of R3W. So W consists of all vectors whose entries sum up to 0. So we want to show that this set with just these two vectors is actually a basis for W. So because the question is related to this set being a basis for W, we're going to use the third property that we saw in the previous slide. So just by the definition of W, any vector in W looks like this, a vector with entries B1, B2, B3, where the sum of B1, B2, and B3 is 0. Then the matrix equation that we want to solve looks like this. So here, the matrix on the left-hand side is the concatenation of the two vectors in S. XY is the vector of variables, and B1, B2, B3 is an arbitrary vector in W. So when we multiply the matrix and the vector on the left, we get this equality of vectors, and just by equation 2 and equation 3, we get that x is minus b2 and y is minus b3 over b2. And these choices of x and y also satisfy the first equation. Therefore, for every b in W, the equation ax equal to b has a unique solution in terms of b2 and b3. So we conclude that S is a basis for W. Now let's focus on a special subspace of Rn, that is Rn itself. Recall that for any n, the set Rn is always a subspace of itself. So the next exercise I have is exactly the same as the previous one. We are given a subspace which happens to be R3, and we're given a set S with three vectors in it, and we have to show that this set S is a basis for R3. So like before, we have to show that for every vector B in W, which happens to be R3, the equation Ax equal to b has a unique solution. So let's begin. So we take the three vectors and we concatenate them, and that gives us a 3 by 3 matrix. And we get the matrix equation where xyz is my vector of variables, and b1, b2, b3 form an arbitrary vector in R3. We multiply matrices on the left to get this equality of vectors. Now, all I have to do is solve for x, y, and z. So we first multiply the third equation by 2, and we subtract it from the first equation. So we get 2x minus 2x, 4y minus 4y, 2z minus 4z. So that gives us minus 2z equal to b1 minus 2b3. Now this gives us z equal to minus 2b3 minus 1 over 2. And then we can take this value of z and plug it in the second equation to get a value for y. And then we can take these values of y and z and we can plug them in the first equation to get a value for x. So what we've seen is that we have explicit values of x, y, and z for every possible value of b1, b2, and b3. Therefore, there is a unique solution for every vector b in W, which again is R3, and therefore the set S of three vectors is a basis of W. So the three conditions that we saw can also be redescribed using just the rank of the concatenation matrix. So if I have m vectors in Rn and A is their concatenation, then this set of vectors is called a spanning set for Rn if the rank of this concatenation matrix A is the same as the height of the matrix. Now, why is that? Because the original condition said that every matrix equation Ax equal to b needs to have at least one solution. That is, it needs to be consistent. So if it needs to be consistent, I would need the augmented matrix of the matrix A and the arbitrary vector b to have a row echelon form with a leading one in every row to the left of the vertical separator line. Otherwise, we're going to have a zero row and then a leading one to the right of the line, and that would make the system inconsistent. And this set is linearly independent if the rank of A is the same as the width of A, and it's a basis for Rn if the rank of A is the same as height of A and width of A. Please do note that these conditions only work for basis of the subspace Rn and not other spaces of Rn. So whenever your subspace of Rn is Rn itself, then these conditions are going to work verbatim, otherwise not. Okay, so using this new found condition for the basis of Rn, we can provide an alternate strategy to exercise 2, which we just saw a few moments ago. There were three vectors and we wanted to show that it was a basis of R3. So the strategy would essentially look something like this. So the concatenation of three vectors is going to be a 3 by 3 matrix because the height of the vectors were 3, so that gives us the height of the matrix. And there were three vectors in S, so that gives us the width of the matrix. Now we have a 3 by 3 matrix. We can compute its determinant, and we're going to get a non-zero number, and that is going to tell us that A is invertible. And because A is invertible, its rank has to be equal to 3. Now, because the rank is 3, and since the height and the width are also 3, we can conclude that S was a basis for R3. So based on the previous rule for Rn, we obtain the following theorem, that a set of vectors in Rn is a basis of Rn if the concatenation of these vectors has rank n. Now, we also know that the rank of an n by n matrix is n if and only if it is invertible, and that gives us another result that the columns of an n by n matrix form a basis of Rn if and only if this matrix is invertible. So what this means is that if you have n vectors, they're going to form a basis for Rn if and only if their concatenation is invertible. And using this theorem, we can provide an alternative solution to exercise 2. So, like before, we start with the concatenation of the three vectors in S, and that gives us a 3 by 3 matrix. We can compute the determinant of the matrix, get a non-zero number, and then conclude that A is invertible. Now, by theorem 2, because it's invertible, the vectors in S are going to form a basis for R3 because the vectors are the columns of the matrix A. So we have just surpassed the entire concept of rank in this strategy. So before I move forward, I want you to think about whether it's possible to apply theorem 1 to write an alternative solution to exercise 1. Now, because the condition for the basis requires that the rank of the concatenation is the same as the height and the width of the concatenation, that just tells us that every basis for Rn is going to have vectors of length n, but they also must be n many vectors. So any basis must have exactly n vectors if you're dealing with the subspace Rn. So for example, if you're given a set of three vectors in R4, then you can confidently say that the set is not a basis for R4 because we need exactly four vectors. And if you're given a set of five vectors in R4, then you can immediately say that the set is not a basis for R4 because you need exactly four vectors. And if you're given a set of four vectors in R4, then you need to do a little bit more work to determine whether it's a basis or not. So another example, if you were to write any basis for R3, you might have different vectors in the basis, but it's always going to be three vectors of height 3. Now this example is a special case of a deep property of basis for general subspaces, and that property or that result is that any two bases for any subspace contain the exact same number of vectors, and we call it the invariance theorem. So this number, of course, is extremely useful because it's independent of the choice of the basis that you're creating. So we give it a special name and we call it the dimension. So as I've said, the dimension of a subspace V is the number of vectors in any basis of V. For example, dimension of R3 is going to be 3 because there's going to be three vectors. We saw this a moment ago. And if W is a subspace of three vectors whose entries sum to 0, this is a subspace that we dealt with in the first exercise, then its dimension is going to be 2 because we only need two vectors to form its basis. And if we define V to be the subspace of three vectors whose entries are all the same, then its dimension is going to be 1 because the basis for such a subspace only contains one vector. So you can generate any vector in a linearly independent way by just taking multiples of the vector 1, 1, 1. So the last thing I want to mention before ending this episode is that this algebraic definition of dimension, depending on the number of vectors in a basis, actually coincides with the geometric notion of dimension as well. So the origin, that is, the set containing the zero vector in R2 or R3 or any other Rn is always a subspace of dimension 0. A line through the origin is always a subspace of dimension 1, and a plane through the origin is a subspace of dimension 2. And with this, I would like to end this episode. Hopefully things were clear. I will see you guys soon. Until then, happy learning.